Now see refraction at a curved surface. So you can assume a curved surface. So this is the interface of the two mediums. This is tensor medium mu2 and this is error medium mu1. Take that mu2 is greater than mu1 for example. Take principal axis, put the name for this P, and object is somewhere here, it is located, object O. The ray which is incident on the surface, which is coming from the object from here to here, it is incident on the surface with an angle. Suppose you can draw a normal on the surface. If you draw normal on the surface, it will be cut the principal axis somewhere. That point what we call center of curvature. Suppose you can take at a point M, this normal drawn on the surface is here, touches the surface here. That is what you call center of curvature. You know, light ray enter from rarer to denser. Here mu1 is less than mu2, rarer to denser. What happens? It bends towards to the normal. If this is the normal, it bends towards to the normal. So due to that, what I get, the ray is refracted like this, like this. So where refracted ray touches the principal axis, there image forms. Here it forms image. Suppose take angle of incidence is I. This is a refracted angle R. Refracted angle. So what about distance? From here to here, object distance U. And here to here, image distance V. And here to here, that is between center of curvature and P, that is radius of curvature R. To get relation between object distance, image distance and radius of curvature, first you take the here angles. Here you can assume that this is alpha and that this is beta, and this angle you can take it as gamma. According to Snell's law, what you can write? Where light enter? From rarer medium to denser medium, so you can write mu 1 to 2 is equal to mu2 by mu1, which is equal to sine of incident by sine of refracted ray. For very small angles, we can write this approximately here I by R we can write. I by R we can write. Suppose using this triangle, you see OMC, using triangle OMC, we can write I is equal to alpha plus gamma. Why? Because exterior angle, I is exterior angle and alpha and gamma are interior angles. So you can write I is equal to alpha plus gamma. Similarly, R is equal to refracted angle, R is equal to. Suppose if you draw a perpendicular foot here, this is a point D. Of course, there is no much difference between point P and D. Both are same only we can consider. But here we are drawing a perpendicular foot. And what about this total angle? That total angle here to here, this total angle is 90 minus beta, because here beta angle is there, here 90. And from here to here it is beta 90 minus gamma. Difference of those two gives R. What is R? It is gamma minus beta we get. Gamma minus beta. We can substitute these two values there. Suppose you can take mu2 by mu1 is equal to, in place of I, what you can take? Alpha plus gamma by, in place of R we can take gamma minus beta. And you can cross multiply. What you can write? Mu2 into what is gamma. Suppose you can take for very small angles, sine theta is equal to theta, and if you want that you can write as tan theta also. If theta is very small, we can write like this. Similarly, in place of gamma, what you can write? Tan gamma we can write. So mu2 into tan gamma. What is tan gamma? Opposite by adjacent. Opposite is MD by adjacent is CP. MD by CP. Minus beta is there. In place of beta, what you can write? For tan beta, opposite MD by IB. This over. Now this. Send mu1 this side. Mu1 into. What is alpha? This side. Tan alpha is equal to opposite MD by adjacent, that is OP. MD by OP. Approximately we are taking P and D are same. Now, in place of gamma, already we know in place of gamma what you can write? MD by CP. We can write. MD is common, cancel that, and mu2 by what is CP? CP is nothing but radius of curvature, which is back side of the curvature. And you know, front side of the curvature, whatever the values you are measuring, that is negative. Back side we can take it as positive. So it is plus R only. Minus, in formula minus is there. Mu2 by IP. IP nothing but image distance. IP from here to here, image distance. That is V. Back side only plus, but in formula we are negative. That's why keep negative like that. Is equal to mu1 by OP. This is mu1 by OP. OP nothing but object distance. Object distance is front side. Front side means you can take negative. That's why minus U you can write. And after that, plus mu1 by CP. CP nothing but R, anyway it is positive. Bring U and V terms one side and R terms other side. What you can write here? Mu2 by V, bring this side, that is mu2 by V minus mu1 by U is equal to, here what you can write? Mu2 minus mu1 by R. We are sending this that side and that we are bringing this side. And this is the expression for refraction at curved surface, or relation between object distance, image distance, and radius of curvature of the interface of the mediums. So here the curvature is like a convex surface, that's why there you get plus R. Suppose if a curvature is like this, then there you get minus R. Here image forms on back side, that's why you get plus V. Suppose if image also front side, you can take, in some cases it is possible, and that also you can take minus here in this formula. Now see, magnification and refraction at a curved surface. Magnification, we have different types of magnification, and transverse magnification, longitudinal magnification, aerial magnification, like that we can take. First we'll see about transverse magnification. Suppose you can take here a refracting curve, a refracting surface. So this is denser media you can think, which is having refracting index mu2, and this having refracting index mu1. And this is the principal axis. Object OJ. Height of the object is HO. Suppose you can consider a ray of light is incident at the center of the refracting surface. Nothing but you can take at the pole, you can think here. This angle is what we taken as incident angle, because you see this is the normal at that point. With respect to normal, the incident ray make an angle I, and it will be refract. You know, here we are taking mu2 is greater than mu1, means light ray enter from rarer to denser, so it bends towards to the normal. Due to that, what happened? It refracted like this. So this is a refracted angle, and somewhere here it forms image. IG is the name of the image, and height of the image is HI. Incident angle and refracted angle we get. Suppose if you want to get relation between height of the object and image, or distance of the object and distance of the image. What is the distance of the object from here to here? Distance of the object U. This is the distance of the image V. Now what you can take here, tan I is equal to, according to this triangle, that is according to triangle OJP, tan of incident angle is equal to opposite by adjacent, that is the height of the object by image distance u, object distance u. From this triangle that is PIG, from triangle PIG, we can write tan R is equal to, here also opposite by adjacent, HI by V. Suppose if you take ratio of these two, what you get, tan I by tan R is equal to, approximately if I and R values are very small, you can write this as a sin I by sin R, which is equal to mu2 by mu1. Because you know that refractive index formula sin I by sin R, and where light enter from first medium to second medium, so refractive index of second medium by first medium we can write, which is equal to, from this what you can write, tan I and tan R. From this we can write here mu2 by mu1 is equal to tan I, nothing but height of the object by u into tan R by tan R. So write reciprocal, V by height of the image. But what is transverse magnification? Perpendicular to principal axis. Transverse means perpendicular to principal axis. What is the height change in the object and image? So how many times our image size is more when compared to object? That is what we call transverse magnification or lateral magnification. So what is the formula for transverse or lateral magnification? MT is equal to, transverse magnification is equal to height of the image by height of the object. Height of the image by height of the object. That means these two you can send that side. This goes to numerator and this goes to denominator. Similarly, you can write mu2 by mu1, also bring this side. So what you get from this? And V by U into mu1 by, you see this mu1 and mu2 you can bring. Mu1 by mu2. Like this we can calculate transverse or lateral magnification. So height of the image, suppose for example here real image, real image means magnification should get negative value. So here height of the image is negative and height of the object is above principal axis positive. And here how we are getting? Here also should get negative. What is object distance? Back side of the surface is positive, U is front side of the surface, that is negative. So here you can take V is negative and U is positive. But there in the magnification of the mirror, what you get? Magnification of the mirror, transverse magnification is minus V by U, we write. Reason, both U and V are forming the same side, both negative, and but in real image, you should get a negative magnification. That's why they took negative there. But here in place of refraction of curved surface, no need to take here minus. Height of the image by height of the object, which is equal to mu1 by mu2 into V by U. Okay. And second type of magnification is aerial magnification. Aerial magnification, in case of mirror already we discussed, that is m t square. This square of transverse magnification. What is transverse magnification? That is here mu1 by mu2 into V by U whole square. This is aerial magnification. What is aerial magnification? Suppose you can take a refracting surface. An object is there which is having some area like this. And what is the size of the image? Size of the image, area of the image. Area of the object, AO you can take. Area of the image is AI you can take. Then from this, what you can write? The area of the image is m times of area of the object. So area of the image is equal to m nothing but you can write mt square AO object, or mt square you can write mu1 by mu2 into v by u whole square AO. This is the final area or area of the image we get. Other type of magnification is longitudinal magnification. Suppose you can take an object is placed here on the principal axis. This is the object, and length object you can take it as LO, and neither end of the object is at distance u1 from the pole, and for distance is u2 distance. Both are object distance only, but neither end and for end of the object. And how we are getting image means, so you are getting image here, so you may get like this, you get image formation. Nearer end forms image for distance, that is v1, and for distance object forms a nearer, that depend upon the situation where to where light ray is going, from rarer to denser or denser to rarer. And here we are taking that mu2 is greater than mu1, that means light ray enter from rarer to denser. In that case, in place of u1 object is u1 is object means v1 is the image. If u2 is object, v2 is the image you get. This is the length of the image from here to here, length of the image, and this is the length of the object. And different positions, suppose object distance is changing from here to here because of length, linear length of the object, position changes. Position changes means magnification also changes here. That's why I get a different shape like this we get. Now what we need here, longitudinal magnification. What is longitudinal magnification? Magnification longitudinal is equal to length of the image by length of the object. What is the length of the image? Here you can write so v1 minus v1 is greater, that's why you can write v1 minus v2 by u2 minus u1, which is nothing but a change in v by change in u. You can write, you can take minus also, because here reverse we are taking, that is the reason. And here you can write if you want to write reverse, you can write v2 minus v1. Yeah, here you get minus here, du by dv by du, change in image distance by change in object distance. So otherwise change in v nothing but length of the image by change in u is nothing but length of the object. And we know using a formula, that is the refraction at curved surface formula. What do you get? Refraction at curved surface, that is mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. Now if you differentiate both sides with respect to x, but because we need a dv by du, to get that what we are doing, we are differentiating with respect to x. Suppose you can take use the formula d by dx of y power n is there, then what you can write, n into y power n minus 1 into dy by dx we have to write. Why? Because we are doing with respect to x differentiation, but here y terms is there. Suppose here also x is there, then only this part we are getting, n into x power n minus 1 only. But here y is there and differentiating we are with respect to x. That's why I use this formula. To apply that formula, you can write mu2 and v is bring it to numerator. So d by dx you can apply, d by dx of v power minus 1, denominator bring it to numerator, minus, in formula minus is there, minus d by dx of and mu1 also there now, that we'll write first outside, then we'll write this, minus mu1 outside and d by dx of u power minus 1, denominator you can bring it to numerator, that is equal to d by dx of mu2 minus mu1 by r. Now see differentiation, what you get, mu2 we can write outside, In place of n, what do you have? Minus 1. So minus 1 into y power nothing but v power minus 1 minus 1. So minus 2. So what do you get? Minus v power minus 2 we get. So into here, into what you get right after this, again you have to write dy by dx now. So nothing but here dv by dx you can write. Now here minus mu 1 into, same this also, minus u power minus 2 into du by dx we get. This total is constant. Differentiation of constant is 0 you get like this. This minus or minus you get plus and bring one side. So what we need actually, we need dv by du. So dv, and first you send the term u2 by v square, of course minus is there, into dv by dx, which is equal to, if you send this side, what do you get? Mu 1 by u square into du by dx. Here what we need? Minus dv by du we need. So magnification, longitudinal magnification, ml is equal to minus dv by dx, sorry, dv by du is equal to dx, here dx get cancelled, and what do you get here? Mu 1 by mu 2 into v by u whole square we get. This is a longitudinal magnification formula. We can write like this. Longitudinal magnification. Now we'll see speed of the image in transverse direction. For example, you can take object is going up like this. So at any position, height of the object is HO, and then image is going downward, depend upon the situation, where to where light enter, or which type of surface is this, convex or concave surface. Depend upon that, it may move sometimes upward or sometimes moves downward. Example, you can take it moves downward, or image moves downward. Now, what is the velocity of the object and what is the velocity of the image? What is the relation between these two? First of all, transverse magnification you can see. Why? Because perpendicular to principal axis, so whatever the magnification, that what you call transverse magnification. Transverse magnification mt is equal to height of the image by height of the object, which is equal to mu 1 by mu 2 into v by u. This is the transverse magnification formula. From this height of the image, you can write height of the image equal to m transverse into height of the object. What you get if you differentiate both sides with respect to time? That is a change in height of the image by height or change in time. Nothing but a d height of the image by dt is equal to mt to dh object by dt. This is nothing but speed of the image perpendicular to principal axis. That is velocity of the image or speed of the image is equal to mt into speed of the object. And here mt, in place of mt, this is the one of the formula, and in place of mt we can write this also. So we can write speed of the image perpendicular to principal axis or transverse velocity is equal to, in place of mt you can write mu 1 by mu 2 into v by u into velocity of object. Like this we can write. So when object is moving, and here perpendicular to principal axis, and image also moves perpendicular to principal axis, this is how we are getting relations here. We already discussed about speed of image and object transverse to principal axis and nothing but perpendicular to principal axis. Now we'll see speed of the object and image along principal axis. That means if this is the interface, and the object is moving here and image also moves here. With what speed object is moving, that we can represent VO, and with what speed image is moving, VI. What is VO? Changing the position of the object. U is the position of the object by changing time, that is speed, and changing the position of the image, dV by dt. To get relation between these two, use a relation between object distance, image distance, and radius of curvature formula. That is mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. Both sides differentiate with respect to time. Nothing but you can write mu2 outside and d by dt of v power minus 1. And denominator we are sending into denominator. In formula minus is there, minus mu1 outside, and you can apply d by dt of u power minus 1. And here d by dt of mu2 minus mu1 by r, that we get. We have one formula, one relation is there. If you are differentiating d by dx of y power n is there, you get n into y power n minus 1. Again, you have to write dy by dx. Doing with different variable, if you are doing differentiation, finally you have to write dy by dx also. Similarly, we are doing with respect to time, but here u and v are there. So, which are variables? U and v are variable. So, for that, what you get differentiation here, mu2 we can write outside. In place of n, minus 1 is there, so minus 1 into v power minus 1 minus 1. So v power minus 2 minus v minus 2 we get into dv by dt minus, here this is in bracket, you can take better, minus mu1 in bracket. Similarly, how we are getting v power minus 1, here u power minus 1 is there, minus u minus 2 du by dt we get, which is equal to 0 because it is constant. This total is constant, differentiation of constant is 0 we get. And from that, what is this value? dv by dt is distance, speed of the image. So we can write here mu2 by v square minus into velocity of the image. This is velocity of the image, and send this that side. What do you get? Here minus minus get cancelled, here also get minus 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 get cancelled, but we are sending this side, that's why again you get minus. Here mu1 by u square. What is du by dt? Changing the position of object by changing time, nothing but velocity of the object, vo we can write. From this, what you can write? Velocity of the image is equal to, here velocity of the image is equal to vi is equal to minus get cancelled, mu1 by mu2 into v by u whole square into v object. Don't get confused here, v and u are velocity of the positions of the image and object. Vi and vo are the velocity of the image and velocity of the object. If object is moving along principal axis, then image also moves along principal axis. With what velocity is moving? It is mu1 by mu2 into v by u whole square into vo, velocity of the object or speed of the object. Now see principal foci and focal length of a refracting surface. You can take this the refracting surface curvature, you can take it as r. This side refractant index mu1 and here refractant index mu2. So how they define principal focus? Suppose for example, you can take here a parallel beam of light is incident. A parallel beam of light is incident. This you can think like principal axis. This all the rays are converges at a particular point. This particular point what we call principal focus. The distance between the pole and principal focus that we take it as a focal length. This is actually second focal length. Why? Because we are getting in the second medium. So that you can take it as f2. The distance from here to here is f2, nothing but image distance only. Why? Because here you see object, the rays which is coming from infinite means you can think that object is at infinite distance. U is equal to infinite. And what is V? V is equal to f2, of course, plus f2 because of backside of the mirror. And here negative. So what is the general formula for object image distance of curved surface, refraction of curved surface? That is mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. We can take here mu2 by where V forms, that is at f2 distance, and U is infinite, 1 by infinity is 0, so don't take that. That is equal to mu2 minus mu1 by R. From this, what you get? That is f2 is equal to R mu2 by mu2 minus mu1. This is the focal length in the second media, so this is the second focal length we can get. Suppose same thing if they take a reverse. Suppose where you have to place the object to get image at infinite distance. In that case, what you get this formula, how this formula is modified, and here you can take and second case. So here interface here mu1 and mu2. This is the principal axis, and where you have to place object. Where you have to place the object, suppose somewhere here object, and from object you get a rays like a diverging rays you can think, and after refracting they should go parallel to the principal axis. That means the image where it forms, it goes to form at infinite distance. Here V is equal to infinite and U is equal to f1, first focal length. In first medium, focal length is a distance between the focus point. You can take it, this is f1 and this is f2 you can take, and here f1. Now what do you get relation from these two? We get a relation here. Use this equation only, mu2 by infinite, so this becomes 0 minus mu1 by f1 is equal to mu2 minus mu1 by R. From this what you get? f1 is equal to minus mu1 R by mu2 minus mu1 we get. From this we get, for a refracting surface we have two focus points, f2 and f1, and two focal lengths, second focal length and first focal length. Now let's see what is the relation between f1 and f2 using these two equations. So take ratio f2 by f1, what do you get? This by this, f2 by f1 is equal to, here R mu2 by, here mu2 minus mu1, here minus mu1 R by mu2 minus mu1. R by mu2 minus mu1 get cancelled. What you can write? It is minus mu2 by mu1 we can write. From that equation, bring this R and mu2 minus mu1 this side. What you get? Mu2 R by mu2 minus mu1 into V minus mu1 R by mu2 minus mu1 into U, and that side you get 1. That we are setting this side. You see that mu2 R by mu2 minus mu1 is f2, so we can write f2V plus, but because minus mu1 R by mu2 minus mu1 is f1, that's why f1 by V not V, U is equal to 1. We get another relation between object distance, image distance, and focal length in first medium, focal length in the second medium. Two focal lengths. Now see power of refracting surface. So we already know the relation between two focal lengths. Suppose you can take a refracting surface here, refracted as mu1 and mu2, and this side principal focus is f2 and this side principal focus is f1. This distance is f1 focal length and this side distance is f2. Now what is the power of refracting surface means? It is a reciprocal of reduced focal length. Nothing but power they define like this. It is a reciprocal of reduced focal length. Nothing but you can write mu1 by f1 or otherwise which is equal to, from that equation what you can write minus mu1 by f1 is equal to mu2 by f2 we can write. This what we call reduced reciprocal of reduced focal length. Actually reduced focal length means f1 by mu1 and f2 by mu2 are reduced focal lengths. Reciprocal of that they define as power of reflecting surface. Nothing but from this what you can write from using those two equations, that we can write it is mu2 minus mu1 by r we can write. This is the power of refracting surface.